All right, so in this example here, we're going to take a look at our modal superposition. Now, as an overview here, we have some excitation coming in here. This could be from free vibration over here. You can see we have our P, our U naught, our U naught dot over here. And this is going into some structure. Now, in particular for this problem here, we're going to be dealing with a shear building is what we're going to be looking at here. But if this could be any n number of degrees of freedom, we've seen 2-story, 3-story, and we can keep going up to 4, 5, 6, 8, however many stories there are. Within that, for this mode undamped, we're going to have our general equation here. We have M, our mass matrix, our U double dot plus K, our stiffness matrix, times X is equal to P over here. And then from this, we're going to get a response. So our response is going to be in the form right here that we see as our U of T is equal to the summation from I equals 1 to some n of our mode shape here times the sine of our natural frequency plus phi sub I there. So the first step with any of these mode superposition problems is to obtain our natural frequencies. So we're going to go through and try to solve for our natural frequencies and our natural modes for this undamped system. Now we're talking about natural frequency and natural modes. We have our omega sub I for our natural frequency and our phi sub I for our mode shape, depending on which one we're looking for. In this particular problem, we're going to deal with a two-story shear building, so we're going to have omega 1, omega 2, and phi 1 and phi 2 for this here. Now, for our natural frequencies and modes of the undamped systems, we have this algebraic eigenvalue problem here, which we are given to us in our textbook now as equation 11.3. So we can see this involves our K, our stiffness, our natural frequencies, and our mode shapes, and our mass matrix right there. So everything that we're given in the problem and everything we need to solve for is going to be able to utilize this governing equation here from our textbook. And this will give us our eigenpairs. So for our example problem here, as I mentioned, we're going to be dealing with a 2-story shear frame building. So we can see here's our problem statement and our setup page right here. So this is our example right here. We can see there's 2 stories right there and there. We can see that our M1 is equal to 1. Our M2 is equal to 3. We have our K1 is equal to 1 and our K2 is equal to 2. And we also have our U1 and our U2 right there. Now we want to take all this information from the given diagram here and place it off to the side so we have a quick place to reference back to it that's neat and organized. So I create this given section over here where I say my M1 is equal to 1, my M2 is equal to 3, my K1 is equal to 1, and my K2 is equal to 2. So with this information here, what we want to do now is create our matrices. So we come up to our general form right here for our mass matrix and our stiffness matrix. Now the general form for our mass matrix, we can see here, this is a 2x2 matrix. We have our M1 and our M2 on the diagonal here, and we have 0 and 0 there, where our M1 is 1 and our M2 is 3. So we can put those directly in there, and we end up with M is equal to 1, 0, 0, 3. So this is our mass matrix right there. Now the next thing that we want to do is create our stiffness matrix. So our general format for our stiffness matrix here is another 2x2 matrix, and we have a K1 plus K2 is this element here. So K1 is 1, K2 is 2, 2 plus 1 is 3. There's our first term there. Then we have a negative K2 right there. We go to our K2 is 2, so this is a negative K2 there, a negative K2 right there as well. And last we have K2 down there, which again, recall, is 2. So we now have a 2x2 matrix for our stiffness as well. So we have our mass matrix and our stiffness matrix. So from all this given information, our problem statement, our given diagram, what are we asked to solve for? Well, they want us to solve for our natural frequency and our mode shape, or our omega, and our phi values there. For this case here, again, we only have 2, so it'd be omega 1 and 2 and phi 1 and 2 here as we solve for our omega sub I and our phi sub I right there for natural frequency and our mode shape. So as we begin our solution here, we want to bring over our mass matrix and our stiffness matrix here that we calculated on our first page there, and recall that what we're looking for in this problem is to find our natural frequencies and our mode shapes. So we can go back and reference that equation 11.3 from our textbook here for our eigenvalue equation here, and we recall that we have our K minus our omega squared M. So we want to take the determinant of that. So we want to plug in our K matrix here. We want to multiply through our omega squared by my M matrix. So I'm going to take a minute here and just go through this right here and do this part. So if we were to take an omega squared and multiply by our M, we end up with this relationship here. We multiply through by omega squared times our mass matrix right there. And what we end up with is this 2x2 matrix here. We have omega squared, 0, 0, and 3 omega squared. So now we want to say K minus that. So here's our K matrix right there. So 3 minus omega squared is 3 minus omega squared. Negative 2 minus 0 is negative 2. Negative 2 minus 0 there is another negative 2. And then we have 2 minus 3 omega squared is right there. So now I have a new 2 by 2 matrix by subtracting my omega squared m from my K matrix. So the next thing I want to do is take the determinant of that. So we can do this by cross multiplying. I can say my 3 minus omega squared times 2 minus 3 omega squared right there, minus negative 2 minus negative 2, which is a minus 4. So from the first part, when we come across this diagonal right here, I end up with this relationship there. So now from this here, what I can do is I can FOIL that out. First, 3 times 2 is 6. Outside, we have 3 times 3 omega squared is 9 omega squared. Inside is omega squared times 2, which is 2 omega squared. Last, we have negative omega squared times negative 3 omega squared. When we do that out there, we have 3 omega to the 4th positive, and then our negative 4 is simply our negative 4. So we end up with this relationship here of 6 minus 9 omega squared minus 2 omega squared plus 3 omega to the 4th minus 4. Now we can combine and simplify. My 6 and my 6 go together, and in purple here I have my omega squareds go together. So we end up with 2 minus 11 omega squared plus 3 omega to the 4th. Rearrange a little bit here, so I end up with 3 omega to the 4th minus 11 omega squared plus 2 is equal to 0. So I write that down there. Now I can factor this out. You can try to use a quadratic. You can plug this into MATLAB. You could run this on your calculator. Simple quadratic equation. There's even solvers you can use online. We end up with that there. What we end up with when we solve for our omegas squared, we end up with omega 1 squared is equal to 0.192. And omega 2 squared is equal to 3.475. Now if I take the square root of each of those, I end up with omega 1 right here of 0.438 radians per second, and omega 2 of 1.864 radians per second. So now we have the first part of the problem solved, where they asked us to solve for our natural frequencies. From there, the next thing that they need us to solve for is our mode shape. So we take that information here. We have our natural frequencies right here that we solve for. We have our omega 1 squared, our omega 1, omega 2 squared, omega 2 right there. So those are our natural frequencies right there. And we recall over here we have this relationship for K minus our omega squared m from equation 11.3 in our text. And this ended up equaling to our 3 minus omega squared, negative 2, and 2 minus omega squared. So what we want to do now, in order to solve for our mode shapes with this equation here, is to plug in for omega 1 and omega 2 separately. So for omega 1, recall that our omega 1 is our 0.192, or our omega 1 squared is 0.192, and our omega 1 is 0.438. So we come down here, and this is 3 minus omega squared. So for omega 1, our omega squared is that 0.0192. We plug it right there. This is a minus 2 and a minus 2. And we have 2 minus our 3 times omega squared. So 2 minus 3 times our omega squared, or again, omega squared for 1 is 0.192. We can plug that in there, times, now our mode shapes that we're looking for here is equal to, we'll do out our math here, 3 minus 0.192 becomes 2.808. And 2 minus 3 times 0.0192 becomes 1.424. So this now becomes this 2 by 2 matrix times our mode shape right here is equal to 0. Again, according to that equation from 11.3 from our textbook there. We can make an assumption for 1 right there. When we make that assumption, we can then solve over here. And we have this now for a value for our mode shape for Th1. Now we want to do the same type of thing for our omega 2, so we do our second natural frequency right here. So our omega 2 is 1.864 radians per second, so our omega 2 squared is 3.475. So we can plug that in there. When we plug this in again, back to this same equation here, 3 minus our omega squared, or omega squared in this case here is at 3.475, so 3 minus 3.475, negative 2 and negative 2 stay the same there. This is 2 minus 3 times omega squared, where omega squared is still that 3.475. We can plug in there, times our mode shapes Th1 and Th2 right there, plug in, and what we end up solving for when we get our Th2 out of this relationship here using equation 11.3, we get our mode shape for Th2 now of 1, we make that assumption there, and a negative 0.2375 there. So now, circled in both these blue squares here, we have our Th1 and our Th2 for our mode shapes. So all that it asked us to solve for within this problem here is our natural frequencies are omega and our mode shapes phi, which we've done already, but we could take it one step further if it asked us to and double check for orthogonality right here. So I'll briefly go through this, and this is covered in section 11.3 in our textbook as well. Where we go ahead and check for that orthogonality. So we take here and we say, okay, I have the properties of my modes right up here. I have my modal matrix, so the information I found for my Th1 and Th2 I can put into a 2x2 matrix over here of 1, 1.404, 1, and negative 0.24 right there. And I have my omega squared I can put into matrix form right here, another 2x2 matrix of my 0.192, 0, 0, and 3.48. So with that information there, I can then plug back over in here to this key equation right here. So if I plug into this guy right here, and again, we can reference back to chapter 11 in our textbook here. So I take this, and don't forget to take the transpose of this matrix right here from our mode shape. So this is our matrix right here. Multiply it by our mass matrix that we solved for at the very beginning of this problem here. And multiply it by, again, now by my phi right here, which is not transposed there. And when I do that, I end up with an equation right here for a 2x2 matrix right here, where we have 6.9136, 0, 0, and 1.1692. From there, what I want to realize is I want to get my truncated modal matrix so I can follow these relationships here in order to plug in for my modes, my Th1 and Th2, in order to get this matrix right here. So we end up with this 2x2 matrix when I do out this key equation right here for Th1 and for Th2. Plug these guys directly in down here now into this right here and right here. So I end up with this 2x2 matrix right there. And then I can double check my orthogonality over here. So I multiply through by this matrix right here, transpose, times my mass matrix, which is the same mass matrix up here, times this matrix right here, not transpose, do out my math, and I do end up with my identity matrix. So therefore, we did double check that it is orthogonal.